crossing the galaxy sounds like a future problem. It sounds like something technology will solve one day, but physics tells a very different story. It says you may never make it. Not because of distance alone, but because something will kill you long before you arrive. And the most dangerous part is not where you are going. It is what happens to you on the way there. The Milky Way galaxy is vast beyond normal understanding. It stretches about 100,000 light years from one side to the other. Light itself, the fastest thing in the universe, takes 100,000 years to cross it. That is not a number the human brain handles easily. That is not a journey. That is a time scale longer than entire civilizations. Now think about this. The fastest spacecraft ever built by humans would take tens of millions of years to cross even a small part of that distance. That is not a slow trip. That is a completely impossible one for any human life. So naturally, the idea is simple. Go faster, go close to the speed of light. That is where hope begins, and this is where things start to fall apart. Physics does allow strange things at high speeds. Time itself begins to change. As you move faster, time slows down for you. This is not science fiction. This is real, proven, measured. Astronauts already experience tiny versions of it. The faster you go, the more extreme it becomes. At near light speed, something incredible happens. A journey that takes thousands of years from Earth could feel like just years to you. In theory, you could cross huge distances within a single lifetime. This sounds like the solution. It sounds like the breakthrough that makes galactic travel possible. But this is where the real danger begins. Because speed does not solve the problem. Speed transforms the problem into something far worse. The universe does not stay the same when you move through it that fast. Space itself changes. Energy behaves differently. Even empty space stops being empty. Most people think the biggest challenge is building a fast enough ship. That is only the beginning. The moment you reach extreme speeds, everything around you turns hostile. Invisible particles become deadly. Radiation intensifies. The very fabric of space becomes a threat. And then there is your body. Your body was built for Earth. It evolved under gravity, under protection from radiation, within a narrow range of conditions. It was never designed for decades in deep space. It was never designed for centuries. And it was definitely never designed for near light speed travel through a galaxy filled with invisible dangers. Even if you solve the engineering problems, even if you build a perfect ship, even if you find a way to accelerate to incredible speeds, there is still a question that remains unanswered. What kills you first? Is it the radiation slowly destroying your cells? Is it microscopic particles hitting your ship with explosive force? Is it the extreme energy required to keep? Are you moving? Or is it time itself separating you from everything you have ever known? Because here is something most people never think about. Even if you survive the journey, the universe you left behind will be gone. Thousands of years will pass outside your ship. Entire civilizations could rise and disappear. The night sky you return to will not be the same. Your home will not be the same. So this is not just a story about distance. This is a story about limits. The limits of the human body, the limits of technology, and the limits written into the laws of physics themselves. In this video, you will learn why crossing the galaxy is not just difficult, but possibly impossible. You will see how time, energy, radiation, and space itself turn against you. You will discover the hidden dangers that make even the fastest journey a deadly one. And by the end, you will understand why the greatest barrier is not how far the galaxy stretches, but how fragile human life really is in a universe like this. Welcome to the channel. If you are curious about the deepest truths of the universe and the limits of reality, make sure to subscribe and stay with us until the end. The problem begins with distance. Not the kind of distance measured between cities or planets, but something far beyond that. Even the closest star system, Proxima Centauri, sits more than 4 light years away. That means light itself takes over 4 years to reach it. No human has ever traveled even a tiny fraction of that. Now scale that up. The galaxy is filled with hundreds of billions of stars, each one separated by distances that stretch across empty space. From one side of the Milky Way to the other, the distance reaches about 100,000 light years. That is not a path. That is a barrier. The fastest spacecraft ever built, the Parker Solar Probe, can reach speeds of about 700,000 kilometers per hour. That sounds fast. It feels fast. But at that speed, reaching the nearest star would still take thousands of years. Crossing even a small portion of the galaxy would take tens of millions of years. This is where the idea of extreme speed enters the story. If you cannot survive millions of years, then you must shorten the journey. You must push closer and closer to the speed of light. That is the only way to make the distance manageable within a human lifetime. And physics does offer something strange here. As speed increases, time begins to slow down for the traveler. This effect is called time dilation. It has been measured with atomic clocks. It is real. At very high speeds, time inside the spacecraft moves much slower than time outside. This creates a powerful illusion. A journey that lasts thousands of years for the rest of the universe might feel like just a few decades for the person inside the ship. That sounds like a solution. It feels like the universe is offering a loophole. But the numbers do not fully save you. Even at 90% of the speed of light, crossing the galaxy would still take over 100,000 years from the outside perspective. Inside the ship, time would slow, but not enough to erase the journey completely. You would still face decades, even centuries, depending on the exact speed, and reaching those speeds is not simple. Each small increase requires more and more energy. There is another detail that most people miss. Acceleration itself takes time. You cannot instantly jump to near light speed. The human body can only handle limited acceleration. Too much force and blood flow fails. Organs begin to shut down. Even at safe levels, it could take years just to reach the target speed and years more to slow down at the end. So the journey stretches even longer. Distance does not just sit there waiting to be crossed. It forces you into a dangerous trade. To survive the trip, you must go faster. But the faster you go, the more extreme the conditions become. Speed begins to change the rules of reality around you. It increases energy, magnifies tiny particles, and exposes you to forces that do not exist at lower speeds. The deeper you push into the galaxy, the more the universe resists. Speed changes time. This is not a theory built on guesses. It has been tested again and again. Atomic clocks flown on airplanes tick slower than clocks on the ground. Particles moving close to the speed of light live longer than they should. Time itself stretches and bends when motion becomes extreme. For a traveler, this effect becomes powerful. As the ship moves faster, time inside begins to slow down compared to the outside universe. At half the speed of light, the difference is small. At 90%, it becomes noticeable. At 99%, it becomes dramatic. Years outside can shrink into months inside the ship. This sounds like a breakthrough. It feels like a way to escape the limits of distance. From the traveler's point of view, the galaxy seems to shrink. The path ahead appears shorter. The journey begins to feel possible within a human lifetime. But there is a hidden cost. The closer you move to the speed of light, the more energy you need. Not in a simple, steady way, but in a rapidly increasing curve. Each tiny increase in speed demands far more energy than the last. Going from 0 to half the speed of light is difficult. Going from 90% to 99% is far harder. Pushing even closer becomes almost impossible. At extreme speed, something strange happens. The energy required starts to grow without limit. It does not just become large, it becomes unreachable. To actually reach the speed of light, you would need infinite energy. That is not a technical problem. That is a wall built into the laws of physics. There is another effect that makes things worse. As speed increases, the mass of the moving object effectively increases as well. This is not the everyday kind of weight, but a resistance to acceleration. The faster you go, the harder it becomes to go even faster. It feels like pushing against an invisible force that grows stronger with every step. This means the final stretch toward light speed is the most difficult part. It demands enormous energy for almost no gain in speed. You burn vast amounts of fuel just to add a tiny fraction of velocity. The ship fights against the universe itself, and there is no way around it. No engine design can bypass this limit. No clever shortcut removes it. The equations that describe space and time all point to the same conclusion. Light speed is not just fast, it is a boundary. You can get closer and closer, but you can never cross it. This creates a strange trap. You need extreme speed to survive the journey across the galaxy. But reaching that speed demands energy that borders on impossible. And even if you get close, you are still not fast enough to fully escape the effects of time. So relativity offers hope, but only partially. It reduces the time you feel, but it increases the cost you must pay. And as the ship pushes harder and harder, something else begins to change. The space ahead is no longer calm or empty. It starts to turn into something far more dangerous. Space looks empty. From a distance, it feels calm and silent. There are no walls, no weather, no visible danger. But this is an illusion. Space is filled with particles, tiny ones, invisible ones. And at low speeds, they seem harmless. At near light speed, they become deadly. Every atom floating in space turns into a projectile. Hydrogen atoms are the most common. They are everywhere, drifting between stars. At normal speeds, they pass by without doing much. But when your ship moves close to the speed of light, each one carries enormous energy. The faster you go, the harder they hit. A single hydrogen atom striking the front of a spacecraft at near light speed can release energy similar to a small explosion. Not because the atom changed, but because your speed transformed it. Motion turns harmless. Particles into high-energy impacts, now multiply that by billions. Interstellar space is not packed, but it is not empty either. Even in the quietest regions, there are thousands of particles in every cubic centimeter. At extreme speeds, your ship would be hit constantly. Not once in a while, but every second. A continuous storm of invisible impacts. Then there is interstellar dust. These are slightly larger particles, still microscopic, but much heavier than single atoms. At near light speed, they become something far worse than dust. They act like bullets. Some calculations show that even a grain the size of a speck could hit with the force of a bomb. One impact could tear through shielding, damage critical systems, or even destroy the ship entirely. There is no easy way to see them coming. They are too small to detect at long distances, too fast to avoid. Even advanced shielding faces limits. Every layer you add increases the mass of the ship. More mass means more energy needed to accelerate. The same problem returns again. And then there is radiation. At high speeds, radiation does not stay the same. The universe ahead of you begins to shift. Light from stars compresses into higher energy wavelengths. Visible light can turn into ultraviolet. Ultraviolet can become X-rays. X-rays can become gamma radiation. This effect is called blue shift. It means that even harmless background light becomes dangerous. The cosmic microwave background, a faint glow left over from the early universe, normally sits at a very low energy. At near light speed, it shifts into deadly radiation. It starts to behave like a constant beam of high-energy particles hitting the front of your ship. This creates a wall of radiation in front of you. Inside the ship, shielding must block not just particles, but intense radiation as well. Over time, this radiation damages materials. It weakens structures. It breaks down electronics. And most importantly, it damages living tissue. DNA begins to break apart. Cells lose their ability to repair themselves. Cancer risk rises sharply. Long exposure becomes lethal, even if every other system works perfectly. So space changes completely. It stops being a silent void. It becomes an active threat. Every direction hides danger. Every second adds more damage. And even if the ship somehow survives this constant assault, the human body inside faces a much slower, quieter kind of destruction. The ship can be engineered. The systems can be reinforced. But the human body is far more fragile. It carries limits that technology cannot easily fix. Radiation is the first silent threat. It does not always kill quickly. It works slowly, quietly over time. High-energy particles pass through the body and damage DNA. Cells try to repair the damage, but the repairs are not always perfect. Errors begin to build. Mutations spread. Organs start to weaken. Astronauts in low Earth orbit already face this risk. Even with protection from Earth's magnetic field, their exposure is higher than normal. On long missions, their risk of cancer increases. Now remove that protection. Move into deep space, then increase the speed until radiation intensifies from every direction. The damage multiplies. There is also a lesser-known effect. Radiation does not only increase cancer risk, it can affect the brain. Studies on animals exposed to cosmic radiation show changes in memory and behavior. Neurons become damaged. Connections weaken. Over time, this could affect decision-making, focus, and emotional control. So the danger is not only physical, it is also mental. And then comes isolation. A journey across the galaxy is not a mission that lasts months or years. It stretches into decades, possibly longer. Even with time dilation, the crew would still experience a long passage of time. They would be cut off from Earth completely. No real-time communication, no return, no connection to anything familiar. Humans are not built for that level of isolation. Experiments on Earth have shown how quickly the mind begins to struggle in confined environments. People in long-term isolation often experience anxiety, depression, and hallucinations. Sleep patterns break down. Motivation fades. Small conflicts grow into major problems. Now extend that to decades inside a closed spacecraft. Every sound becomes repetitive. Every face becomes too familiar. There is no escape, no change, no true rest from the environment. The mind begins to turn inward. Over time, that can become dangerous. Then there is aging. Even if everything else is controlled, the body continues to age. Cells divide and degrade. Tissues lose strength. The immune system weakens. Time dilation can slow this process relative to the outside world, but it does not stop it inside the ship. The traveler still feels every year. Some propose solutions like suspended animation. The idea is to place the body in a deep sleep, slowing biological processes to almost zero. But this remains unproven for long durations. There are risks of tissue damage, brain effects, and failure to restart normal function. Others suggest generation ships. One crew begins the journey and their descendants continue it. But this creates new problems. Maintaining a stable population over centuries is extremely complex. Genetic diversity must be preserved. Social structures must remain stable. A single failure could end the mission entirely. There is also a deeper issue. The human body evolved under very specific conditions. Gravity, atmosphere, temperature, and radiation levels all shaped it. Remove those conditions and long-term effects begin to appear. Bone density decreases, muscles weaken, the cardiovascular system changes. Even after months in space, astronauts require long recovery periods. Now extend that to years or decades. The body slowly drifts away from what it was designed to be, and there is no guarantee it can recover. So even if the ship survives, even if the journey continues, the human inside is under constant pressure, not from a single threat, but from many, all acting at once. And while the body struggles to adapt, another problem grows in the background, one that makes the entire journey even harder to sustain. Every part of this journey leads back to one thing: energy. No matter how advanced the ship becomes, it must be pushed. It must be accelerated. And that requires power on a scale far beyond anything humans have ever used. To reach even a small fraction of the speed of light, the energy demand rises sharply. It is not a straight line. It grows in a curve that becomes steeper with every increase in speed. The closer you get to light speed, the more extreme the requirement becomes. At first, it seems manageable. Chemical rockets already use huge amounts of energy. Nuclear ideas promise more. Fusion concepts promise even more. But when the target is near light speed, all of these systems collapse under the scale of what is needed. The numbers become difficult to relate to real life. To accelerate a spacecraft with any meaningful mass to a significant fraction of light speed, the energy required can reach levels comparable to the total output of a planet over long periods. In some theoretical cases, it approaches the energy output of a star, not just using a star as fuel, but matching its total energy production. This is where the problem deepens. Fuel is not just energy. Fuel has mass, and that mass must also be accelerated. So the more fuel you carry, the heavier the ship becomes. The heavier the ship becomes, the more energy you need. This creates a loop that feeds on itself. More fuel requires more fuel. This is called the rocket equation problem, and it becomes brutal at high speeds. Even advanced designs like antimatter propulsion do not fully solve it. Antimatter contains enormous energy density, but producing it in large quantities is extremely difficult. Right now, humanity can only create tiny amounts in controlled environments, not nearly enough for interstellar travel, let alone galactic travel. There is also the problem of efficiency. No engine is perfectly efficient. Some energy is always lost as heat, radiation, or waste. At extreme energy levels, even small losses become massive. A system that is even slightly inefficient would waste more energy than entire civilizations currently produce. And storing this energy is another challenge. Batteries, fuel tanks, and containment systems all have physical limits. They can only hold so much before becoming unstable or impractically large. At the scale required for near light speed travel, storage itself becomes a major engineering barrier. There are theoretical ideas like laser propulsion, where a spacecraft is pushed by beams of energy from outside. This removes some fuel weight from the ship itself, but even then, the energy source must still exist somewhere. It must still be generated. It must still be controlled over vast distances. Perfect precision, and the required power is staggering. Even a small interstellar probe would demand energy output beyond current global consumption multiplied many times over. A full crewed ship would require far more. Scaling this up to anything approaching galactic travel pushes into territory where even entire planetary systems may not be enough. This leads to a harsh reality. Even if every other problem was solved, even if radiation was blocked, even if the human body could survive, even if speed limits were pushed closer and closer to light speed, there would still be no way to supply the energy required to begin the journey. And even if that barrier could somehow be crossed, another problem waits at the end of the path, where time itself begins to reveal its final consequence. Even if every previous barrier is solved, something else remains. Something quieter, something more unsettling. Time itself. The galaxy is not static. It is not frozen in place like a map. It is alive with motion. Stars orbit the center of the Milky Way. Entire systems drift slowly over millions of years. Clouds of gas collapse and form new stars. Old stars explode and disappear. Nothing stays where it is for long. At human scale, these changes feel invisible. At galactic scale, they are constant. Now consider a journey that takes thousands of years, even under extreme conditions. During that time, the target destination does not wait. It moves. It evolves. The star you aimed for shifts its position. The planetary system you plan to reach may no longer be there in the same form. Some stars live fast. Massive stars burn brightly and die young. They can explode as supernova in just a few million years. That is short in cosmic terms. A destination that seems stable today may become a violent explosion long before arrival. Even smaller stars are not truly permanent. Planetary orbits shift over time. Gravitational interactions slowly reshape entire systems. A stable orbit can become unstable. A habitable world can drift away from its star or fall into it. So the target keeps changing. But there is another layer to this problem. While the traveler moves forward in time, the universe outside moves even further. Thousands of years pass in surrounding space. Civilizations rise and disappear. Signals from Earth fade into silence. Technology evolves. Languages change. Entire cultures may no longer exist in recognizable form. By the time the ship reaches its destination, there may be nothing left that feels familiar. There is a lesser-known effect here. Deep time travel does not only separate you from your starting point, it also separates you from the meaning of your destination. The coordinates may still exist. The star may still be there. But everything connected to it may have changed so much that it feels foreign. Even returning home becomes impossible in a meaningful sense. Earth itself does not remain still over thousands of years. Continents shift, climate, cycles change, species evolve or disappear. Human civilization could transform in ways that are impossible to predict. A traveler returning after a long journey would not return to the same world they left behind. And there is no guarantee that the origin point still exists in the same form. This creates a strange kind of disconnect. The traveler becomes separated not just in space but in time. The ship moves forward, but the universe moves forward faster. Each moment of travel increases the gap between the traveler and everything they once knew. Even communication cannot fix this. Signals sent across such distances arrive too late to matter in real time. Messages become echoes of a past that no longer exists. So even if the ship survives radiation, even if the body survives time, even if energy is found and speed is achieved, the journey still leads to a final problem. Arrival itself becomes uncertain. Across everything explored, one pattern becomes clear. Every attempt to cross the galaxy runs into a barrier that cannot be ignored. It is not a single obstacle. It is many. Distance stretches beyond practical reach. Time bends but does not fully solve the problem. Space itself becomes dangerous. The human body begins to break under conditions it was never designed to survive. And even energy, the foundation of all motion, reaches limits that cannot be overcome with current understanding. Each solution creates a new problem. Faster travel leads to harsher radiation. More shielding adds weight, which demands more energy. More energy leads to impossible engineering demands. Even time dilation, which seems like a gift from physics, only delays the problem rather than removing it. The galaxy does not forbid exploration. It allows movement. It allows curiosity. But it also enforces boundaries that are built into the structure of reality itself. These boundaries are not political. They are not technological. They are physical. That is the key point. Humanity can build better engines. It can design stronger materials. It can develop new theories and new tools. But none of that removes the fundamental rules that govern space and time. The speed of light remains a hard limit. Energy remains finite. Matter remains fragile. And time continues to move forward without pause. This means that the universe may be far larger than human reach. Not because exploration is impossible in principle, but because the cost of crossing those distances becomes greater than what any living system can endure. There is something humbling in that idea. The same laws that allow stars to shine also define how far life can travel. The same physics that creates galaxies also sets their limits of connection. So the true boundary is not a wall that can be broken with better technology. It is not waiting for a future invention. It is already here, written into the fabric of reality. And that raises a final question that lingers long after the science is understood. If the galaxy itself may remain forever out of reach, then the greatest discovery may not be how to cross it, but understanding why it cannot be crossed. If you enjoyed this journey into the limits of the universe, take a moment to like the video. Subscribe to the channel for more deep dives into space, physics, and the hidden rules that shape reality.